So I have a few more words about isomorphism before we jump into the matrix thing. So just to comment, V is isomorphic to W means, well, this means V is isomorphic to W, which is to say that there exists a linear map which is invertible. It's a bijection. And we proved that that inverse also has to be linear, right? And here's a theorem. Isomorphism provides an equivalence relation on the set of F vector spaces. And here's how the proof of that goes. First of all, you have the reflexive property. V is isomorphic to V because you can look at the identity transformation. That's an isomorphism from V to V. Number two, if V is isomorphic to W, then that means we have a bijection which is linear from V to W, an isomorphism. And it's easy to prove that the inverse of an isomorphism is again an isomorphism. Because it's, the inverse of a bijection is again a bijection, and we proved that the inverse of a linear map is a linear map. So there it is. So that then establishes that W is isomorphic to V, which is to say that symmetry of the equivalence relation. And then 3, if we have V1 isomorphic to V2, V2 isomorphic to V3, then that means that there are maps T1 and T2 isomorphisms, right? And we can compose them, T2 composed with T1. That will take us from V1 to V3. And again, the composite of linear maps is linear. And perhaps you remember from a previous course, the composite of bijections is a bijection. If you're not sure about how to prove that, you probably should prove it. Anyway, so the composite T2 with T1 gives us a linear bijection from V1 to V3, which then proves that V1 is isomorphic to V3, which is the transitive property. So we got reflexive, symmetric, transitive. It's an equivalence relation. But I can say more. Remember last class we proved that two vector spaces that were isomorphic had the same dimension. So if you think about it, dimension gives us a way of labeling the equivalence classes. So dimension of the vector space labels the equivalence class of isomorphic vector space. We argued last time V isomorphic to W implies the dimension of V is equal to the dimension of W. All right, and I can even say a little bit more. So I can sort of describe. There's a simple thing we can do here. So if I have V, right, and I have a W over here, right. So suppose this has dimension of V is equal to n, dimension of W also equal to n, right? So how can I prove those are isomorphic directly? Well, one way I can do it is if I've got a basis beta here, and if I've got a basis gamma here, I can look at, suppose, and again, this is over F, so I can look at draw this kind of picture. This is the phi beta map. So down here we're looking at Fn. And then over here, I don't really need to draw a separate copy, but I will just for the sake of discussion. And I can look at the phi gamma coordinate map, right? And for what it's worth, I can take the identity map down here, right? Now I want to build a linear bijection going from V to W. How do I do it? I just use the picture. So to get from here to here, right, what I can do is I can just take this path instead, right? So I need to go the opposite way. So that would be phi gamma inverse. But this map up here, the one I want, so it's kind of funny. You write the last one first, the first shall be last. So phi gamma inverse composed with the identity, and then composed with phi beta. Or better yet, let's just say it's phi gamma inverse composed with phi beta. This gives me an isomorphism from V to W directly in terms of the coordinate maps and their inverse. And so if I have dimension of two vector spaces is matching, I can build an isomorphism from one to the other simply by running through the coordinate maps. Now, that said, or I could just think about equivalence relation, right? This V is isomorphic to Fn, W is isomorphic to Fn, so or by transitivity, and symmetry, I can get that V is isomorphic to W. All right. Anyway, moving on. So this brings us to the problem of how do we describe the matrix of a linear transformation, right? And so let's just get to it. So we have an abstract vector space V, all right? We have an abstract vector space W. And I usually think about this having, you know, the dimension of V being n. I, by default, tend to think about the dimension of W being m, just following our other things we've done so far. And I think about this one having basis beta. I think about this one having basis gamma. I think about being given a linear transformation T from V to W. All right. Well, then I have also, of course, coordinate maps. I've got my phi beta map, and I've also got a phi gamma map over here because I can build coordinate vectors from V. The coordinate vectors from V, well, those fill out Fn. And the coordinate vectors from W, well, those would fill out Fm. Most often this is just Rm and Rn, vice versa. And so down here, we want to build a map that basically this map is multiply by the matrix, we'll call it the matrix of T. But we can't just you can't just use a standard basis, standard matrix notation anymore because we don't have a standard basis in abstract vector space. So what we have to do is we put a beta here and a gamma here to fess up the fact that we're using the beta and gamma basis. All right, and it's pretty simple how we define that. I mean, we start with a vector up here, let's say x, right? That under the phi beta mapping brings us down here to a vector down here, let's say x of beta, all right? And then, well, t maps over here to t of x, that's a vector in W, and that maps under the gamma coordinate mapping to t of x sub gamma, right? And so I want to be able to take this, multiply it by that matrix, and get that. Let me write it down. So what I'm saying is that t of x sub gamma should be equal to this matrix, which we're trying to understand how to define it, like this, all right? So this is the matrix of T with respect to the beta gamma basis. It should satisfy this. This essentially is the definition. What I'm defining here, the only thing that hasn't been defined yet formally is this thing right here. This implicitly defines that. Now, let me be less implicit. Let's just think about how that goes. All right. So, all right. So what happens, excuse me, if we say beta is v1, v2, dot, 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 vn, right? Then, of course, we have that phi beta of vj is equal to ej, all right? In other words, the coordinate vector of vj with respect to the beta basis, again, this is just two different, this and this same thing, different notation, okay? But this is pretty neat because that means that if we look at t, right, if we look at, let's see here, t of vj, right, and we act on that, we look at the gamma coordinate of that, well, that should be equal to this matrix, which we're trying to understand what it is, all right, and then the, that, right, coordinate vector, but this, remember, is just ej. So if we take that matrix times ej, what do we get? We get the jth column of that matrix, right? So therefore, we could also say this about the matrix T, beta gamma, this matrix, this non-standard matrix, if you will. We're trying to understand what it looks like. Here's what it looks like. You take the first thing in the beta basis, you feed it to the map, calculate the gamma coordinates of that. That's the first column. Second column, take the second thing in the beta basis. You feed it to the map. You calculate the gamma coordinates of that. Dot, 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 dot. You take the nth thing in the basis. You feed it to t. Calculate the gamma coordinates of that. There you go. That is yet another way. And okay, so you know a difference between what I have boxed in green and what I'm about to box in red. Well, there's a pretty significant difference, right? What's in green implicitly defines the matrix for t. What's in red explicitly defines the matrix. Okay, great. Let's look at an example. And we'll use the implicit idea to guide our example. So let's see here. How about we look at basis beta 1x squared. And we'll look at the derivative map. That's a pretty good map, d dx. That'll be my t. And so we'll let the w, again, we'll let the w have basis gamma equal to 1x. We'll let it be. So v is going to basically be p2, and w is going to be p1 over the reals, right? So, and then here's the deal. You got to take sort of a generic element in the domain. In this case, a generic element, let's say v, would be a plus bx plus cx squared, right? I feed it to the differentiation operator. I get t of v. That's going to be b plus 2cx, right? All right, great. Then what I have to do is I have to see what happens to those under the beta map, coordinate map, and the gamma coordinate map. Now, typically for these problems, the basis, beta, and gamma are given to you. So you just have to work with them, all right? And a pretty typical problem that I assign you guys is just to find the matrix of t given a pair of bases. You know, so I'm running through a kind of typical example with you here at the moment. So the matrix of, excuse me, the coordinate vector of v with respect to the beta basis, it's just a, b, c. The coordinate vector of tv with respect to the gamma basis, it's, looks like it's just b and 2c, all right? And so whatever it takes to go from here to here, whatever I have to multiply this by to get that, that's the matrix. So let's play a game of fill in the blank. So we're going from, let's see here, 3 dimensions, and over here we've got 2 dimensions. So we're going to look at a 2 by 3 matrix, 2 by 3. Made it a little bit too big. We're multiplying a, b, c, and we're supposed to get out what's supposed to come out. What's supposed to come out is b and 2c, right? And so, well, you know, as I said in the notes, tilt your head and squint. To get b to c here, I make my first column. My first row should be what? It should be, looks like a 0, 1, 2. Oh, I'm an idiot. To get b here, I just need 0, 1, what? I don't need 2 c's, I need 0 c's. Duh. And then to get 2c, I need 0, 0, 2. So there you go. That right there is the matrix of t with respect to the beta gamma basis. This guy, in case you forgot, is v beta. And this over here is t of v with respect to gamma. And that's, so we can't, I mean, you can't write the differentiation operator directly as a matrix multiplication, right? But if you trade polynomials for column vectors like this, then you can find a matrix such that when you multiply the coordinate vectors, it encodes the action of the map at the level of coordinates. So even though an abstract linear transformation of finite dimensional vector space is not directly matrix multiplication, indirectly we can make it matrix multiplication like this. All right, let me show you another couple of examples here. I think I have that same example in the notes, but with a slightly different notation. Let me find it. This is kind of that example. Let's see here. So here I have cubic, so I go P3 to P3 in this example. The derivative operator again. I pick basis 1 xx squared, x all the way out to x cubed. Here's the differentiation operator, right? And so I just calculate, the coordinate vector with respect to beta. V is ABCD. The differentiation operator sends it to B2C3D. So to get from here to there, I multiply by that. All right. So there's another example. Let me just skip back here for a second. No, actually, I'll just go ahead. We'll do a few more examples here in a minute, but since I'm on this page already. Here's some properties that continue to be true for the abstract matrix of a linear transformation. Like the matrix of a sum is still the sum of the matrices, difference is still the difference of the... So these are things we had for standard matrix before. This proof might not make sense yet because well, I'll talk more about this in class probably. I just want to get you guys started on the abstract basis today. So, yes, I'll save the proposition 7.411 maybe next time we meet. Let's just look at another example here right quick. Let's see here. Skipping back actually. Here's another one. If we have, oh, there's a typo in this one too I want to talk about. That L right here is supposed to be an S. Okay, so we're looking at S going from V to W. Actually, it's just a mapping from R2 to R2, R2 by 2 to R2 by 2. And the mapping is, the S is for symmetrization. A plus A transpose is symmetric. Whether A is, whatever the form A has, S of A is symmetric, right? If you look at A plus A transpose, is that symmetric? Well, that's A transpose plus A transpose transpose, which is A. So, yeah, S of A is symmetric. Anyway, if we calculate S of A on a generic matrix ABCD, we get that for its formula. Now, if we use the usual lexicographic basis, E11, E12, E21, E22, the matrix units that we talked about, then the coordinate vector of ABCD is just ABCD. And the coordinate vector of the image, after we calculate the generic, the action, it's 2A, B plus C, 2D. So to get from here to here, I multiply by the matrix S beta gamma, such that that happens. And so if you just look at it to get from here to there by multiplying by 4 by 4 matrix, what you want is 2, 0, 0, 0 to get the 2A, 0, 1, 1 to get the B plus C, 0, 1, 1, 0 to get the B plus C, and then finally 0, 0, 2 to get the 2D. So there's that. Example 7.48 is a little bit, I suppose, weirder. This one's kind of, it's not, I mean, it's a kind of strange example, now that I look at it, but it's an example. So 2 by 2 matrices with linear polynomials is what the vector space is. And I'm looking at defining the linear transformation T going from this, this vector space to just 2 by 2 matrices. So the way I'm doing it is I'm evaluating the matrix at 2. So like I'm basically taking X and putting X equal to 2. That's, well, down here is the map. So for this V, this is my generic vector in V. Polynomial, excuse me, a matrix of first order polynomials. Just take X, set it equal to 2. That's the action of the map. So that gets me this. So the coordinate vector of this with respect to the basis, what basis did I give here? Did I ever state the basis? 7. Oh, I say you should be able to find the basis in view of my coordinate formula. Well, whoop-de-doo. All right, so I'll tell you the basis. I was being lazy when I wrote these notes. E11, and then like the next one would be actually X E11. And then E12, and then X E12, and so forth until we get to, E22, and then X E22. That is the basis that I'm using there. Anyway, so there's the action on the generic element, And so the coordinate vector of that is this. And so to get, and so this is an element of our 2 by 2. So the gamma basis, I'm just using E11, E12, E21, E22. It's 4-dimensional space. And so that's why I just list that one, then that one, then that one, then that one. And so how do I get a plus 2b here? Well, I take 1, 2, 0, 0, 0, 0. See, when I multiply that, when I multiply this by that column vector, that gets me the a plus 2b for the first spot, and then and so forth. So that's a little bit kind of a weird example, but anyway, I think it's good to see some weird examples from time to time. All right, well, I have more to say about matrix of transformation, and I'll try to do some more examples tomorrow in the help session, but I think that should be a good start for you guys. By the way, you'll be happy to know that I'm pushing the mission back to Wednesday. So sorry to bury the lead. Bye, guys.